The very first topic that we covered in this class mentioned the binary system, and we actually saw how integers are represented, both negative and positive. So every time we write a decimal in our Java programs, like the number 24 for example, that number is actually represented using the binary system in the computer. In Java, we can perform operations like addition, subtraction, and so forth as we would like our normal algebra to work, but we can also operate on the bits of a particular number. We can take two numbers and perform operations among their bits at the bit level. For example, we can take two bits and perform a bitwise AND operation. If both bits are 1, the result will be 1, otherwise the result will be 0. A bitwise OR operation will result into 1 if at least one of the bits is 1. The XOR will result into 1 if the bits are different. We have 1 and 0 or 0 and 1. As you would expect, the bitwise NOT is very similar to the NOT operation that we see in conditionals, for example in if statements. So when we have a bit that is 1, NOT will turn it into 0 and vice versa. The shift operations are very interesting, and you may be wondering, why do I need to be shifting bits around, left or right? And here is something that will probably help you realize the fact that they are useful. Think of multiplying a decimal number by 10. If we have the number 105 and we multiply it by 10, it is as if we are shifting the number one position at the left and filling a 0 at the end. If we have the number 23.5 and we divide by 10, it is as if we are shifting the number one position on the right and we're moving the decimal place. So multiplying by the base in a number system is equivalent to shifting the digits left or right. When we are shifting left or right the binary bits, then what we're doing is actually multiplying or dividing by 2. These operations are equivalent. Here is a very simple program through which we will see a few binary operations, bitwise operations. Take a look at the way that we have declared variables a and b. When we start a literal by 0x, it means that the representation is hexadecimal. So f1, if we were to write it in the binary, it would be the first 4, the leftmost 4 bits would all be 1, and then we would have 3 zeros and one more 1. So you see, it is as if this is the equivalent binary. Now the binary equivalent for B would be all of the bits 0 except for the rightmost, which is 1. So these are the two binary numbers that we have here. When we print their values, A and B, we will see their values in the decimal system. What we're doing in the lines 13 to 15 is a few bitwise operations. So we're taking the bitwise AND, the OR, and then we are shifting the bits of B left 3 positions. And after that we're just printing the results, which we are going to see in a moment. I have already run the program, the results are right here waiting for us, but we would like to first think about what we expect to see. When we are doing the logical AND between two binary numbers, what will happen is that only the bits that are 1 at the corresponding positions will also be 1 as the result. So if we take the binary AND between A and B, the only position where they both have 1 is the rightmost position. And these are the only bits that will remain 1 at the end result. So we expect this to have the value 1. If we take the OR, it means wherever there is a 1, either up or down, then the result will have 1 at that position as well. So we actually expect to see the result of A here and the result of B here. How about the third one, when we shift the bits of B by 3 positions? So when we shift 3 positions, it means that this one here, it will appear 3 positions further. So it will be 1, 0, 0, 0. This is the binary equivalent, which is actually the number 8 in decimal. As you can see, these are exactly the numbers that we see as a result. The decimal values for A and B is 241 and 1. When we do the AND operation, we actually see the value of B. When we do the OR operation, we get the value of A because of these particular values that A and B have. And when we shift B 3 positions, we will get 8. The final example I would like us to take a look at comes from the Java tutorials, the tutorials provided by Oracle regarding Java. And we're going to take a look at the bitdemo.java. You can look up this particular code and find it on the website. Let's take a look at what we do here, and it is a very useful thing for us to know, a capability that Bitwise operations give to us. We have two numbers, one we call the mask and the other is just the value. The mask, as you can see, declared in hexadecimal notation, has only the last 4 binary bits on. The last 4 binary bits are 1. Now we have some random value for the value. It is also in hexadecimal notation, so each of the digits that you see account for 4 binary bits. When we do the logical bitwise AND operation between these two numbers, what will happen is that only the bits that are 1 at both numbers will end up being 1 in the result. In other words, all the high-level bits that are 0 at the mask will have as a result to make 0 at the result all of the high-level corresponding bits of the value as well. So it is like we say we apply a mask to the value so that we only keep the value of the bits that we care about. In this particular mask, we only want to keep the values of the least 4 significant bits. So the value that will only be on in the result will be 2. So this program will print 2.